this is Charlotte Bascom, and this is my axolotl crosses PowerPoint and explanation. So, so I'm gonna do. Oh, gotta give it a second to load. So what I'm gonna do is I'm gonna explain crosses between two parents and how their babies came out, and kind of explain the percentages that go along with that, and whether our predictions were correct, whether our Punnett squares shows that they were correct, and just kind of overall how everything comes out, how everything looks, and how the babies differ from their parents versus whether they're a mix of both or individual or anything like that. So if this wants to load, there we go. Okay, so axolotl crosses by Charlotte Bascom. So here are our axolotl parents. So on the left, you can see this is parent number 1. She's a GFP albino axolotl, meaning she has no pigment. She's completely white, but she does glow under a black light. That's what GFP means. And then, fun fact, we get the GFP from an injection from octopuses or squids. They have that glow-in-the-dark feature, and that's where it comes into axolotls. And then this is parent number 2 on the right side. He's a wild-type copper, meaning he can make melanin, but he doesn't glow. He's not a GFP. So when it comes to our axolotl offspring, having two parents on complete opposite sides of the spectrum, your babies are bound to come out differently, with one being albino GFP and making no melanin, and the other not having any GFP at all, but making melanin. So GFP albino would be heterozygote dominant, because GFP is dominant but albino is recessive, and copper would be a homozygote recessive, because copper is recessive and there's no GFP in it. So you can see our chart here predicting that we'll have half will be about heterozygous dominant and half will be homozygote recessive. Now looking at our results, you can see that is not correct from the chart. You can see that, so in this top left corner here, we have a copper, or a wild type, which is just like the dad was. It's a regular copper, just like the dad. But the one below it is a GFP copper. So you can see that that dominant gene was brought over from the GFP albino and put into the copper. So now it's GFP copper. Now in our middle here, at the very top middle, we have a GFP leucistic. Now this is where it starts to get a little confusing, because neither of our parents were leucistic. We had an albino, which means no color at all, but leucistic means that there is color, but it is strictly only in the eyes of the axolotl, which is kind of funny, because that means that we had some gene from the wild type mixed with the GFP albino, and you get a GFP leucistic. And then on the very far right, you just have a regular leucistic, no GFP, just regular, nothing like that at all. So why is this odd? Well, this is odd because neither parent was leucistic, but yet some of their babies came out this way. Half of them, in fact, came out GFP, which, going back, you can see half of them came out. You have your GFP leucistic and your GFP wild type, so that's about 50%. 25% came out as leucistic, and 25% came out as wild type. So the 25% wild type is not so strange, because one of our parents was. It just means that those genes completely took over in that situation. But then 25% of them came out leucistic, which is kind of odd, because neither of the parent was leucistic, so there was some mixing of genes there. So we're left with a 25, 50, 25 percentage, which again is quite odd, because we didn't have a leucistic parent, but we have leucistic babies. And if you got rid of the GFP and you didn't look at that, 50-50 is wild type, 50-50 is leucistic. So that was my presentation. I used cross D, I used both those parents, which are back here, and it was just kind of fun to see how mixing two different parents on completely different spectrums of like what you could have for an axolotl. You got some that were like the dad, and none that were like the mom, and some in between, and GFP and all that stuff, and that's just really cool to see.